Okay, question 10 is about the de Broglie wavelength of a particle. They give us the formula for that wavelength, and then they tell us there's a beam of electrons that have a specific energy, and we have to show what their wavelength is. So they're giving us E, we need to find lambda, just need to plug in our constants, Planck's constant and the speed of light, and then divide by the energy, which is in eV. We need to convert that to joules to get units of meter. So just need to multiply by 1.610 to the negative 19 joules per eV in the denominator, and that comes out as roughly 3, and make sure you show a couple of more decimals in that calculation. They like to see that so that they are convinced you know it's that you get the right result. Okay. So a beam of electrons is directed onto the sample of carbon, and we get this. The intensity of the electrons looks like this. So this looks like a single slit diffraction pattern, right? Or a single obstacle diffraction pattern. So remember, the single slit pattern, diffraction pattern, is identical to a single obstacle diffraction pattern. So this is experimental evidence of the wave-like nature of electrons, that they can diffract around nuclei. So just to remind you that that is what this is showing us. And there is a formula in topic 12 that tells us that sine of the angle, diffraction angle, is roughly equal to lambda over d, where d is the size of the obstacle, or the size of the slit. Here it's an obstacle, the nucleus, size of the nucleus. Okay, so we have to just write something about why this is evidence that electrons can behave as waves. So we'll just phrase that along these lines. It looks like an electron undergoes diffraction, or diffracts around a carbon nucleus. It looks like an electron undergoes diffraction when it passes a carbon nucleus. So this implies electrons that have wave-like properties, because only waves diffract. Okay, and in the next question, we now have to work out that angle. So they give us d, the obstacle, the size of a carbon nucleus. So that minimum is given by this formula, which is in the data booklet. We know what the wavelength is, we know what the size of the nucleus is, and that allows us to work out the angle at which we get a minimum intensity, the first minimum of this diffraction pattern, and that is 37 degrees. Okay, so if we lower the energy, then they would be unsuitable, because the wavelength, as we can see, is inversely proportional to energy. So 10 to the 7 is around 10 times smaller than the previous energy, which means the wavelength is going to be 10 times longer. And with such a long wavelength compared to the size of the carbon nucleus, then we won't get diffraction. Okay, last question is the usual calculation for the density of a nucleus, mass over volume. The mass in atomic mass units is just A, and the volume, of course, is 4/3 pi r cubed. We know the radius formula, we plug that in, and the mass number cancels out, and we get a constant value of the density.